And along this sequence, the function must go to 0. Must be exactly 0. Right, so that's what's supposed to happen. Then there exists Sk with sigma k tending to infinity, such that f of Sk is 0, k equal to 1, 2, 3. This forces, via the identity theorem, for f of s to be identically 0. Okay, by the identity theorem, this forces f of s to be identically 0. Contradiction. There is one value. So this is amazing. The existence of a single non-zero value for a Dirichlet series forces a half plane, which is where it is zero free. Okay, so it's nothing to do with the fact that that value converges to f of 1. It's this identity theorem which is forcing it. Okay, now, as I said, once we show that Dirichlet series are analytic functions, the identity theorem is only for, can be said for sequences of Sk which will have a cluster point. And here we are viewing infinity as a cluster point. Okay, so if you want, you can put it on my we will show that Dirichlet series are analytic functions in sigma greater than sigma A. I'm just putting sigma, actually sigma greater than sigma C, ordinary calculator, but right now I'm just putting sigma A. And this, and then the identity theorem can be formulated in terms of cluster points. Okay, you don't need the infinity. There's a sequence Sk which clusters, and that the two functions are equal there, then f of s and g of s are the same. Now, the reason this infinity thing is interesting is that Sk can actually be very far apart. As long as the real part goes to infinity, however far apart they are, you can get an infinite sequence that forces the identity. So it's a little bit hard to believe, but that's how it is. Okay, so now let's look at ordinary convergence of Dirichlet series. Okay, and then I will come back and do Euler product. I'll do ordinary convergence first. So, the half plane of convergence of a Dirichlet series. All right. So we begin with a theorem. Here, theorem 5. Very useful fact. If the Dirichlet series, actually now I should say formal, summation f of n over n to the power s naught, this is only formal, I'm not saying it's convergent, has bounded partial sums. These doors keep closing. Okay. Has bounded partial sums for some s equal to s naught. Okay. Then, in sigma greater than sigma naught, this is a half plane. We have, like the Cauchy criterion, summation f of n over n to the power of s between a and b. We get an estimate on the tail is less than or equal to. Well, I should probably have said what bounded partial sum. is less than or equal to 2m over a to the power sigma minus sigma naught times 1 plus absolute value of s minus s naught divided by sigma minus sigma naught, where partial sums bounded by this m. So that's what I mean by, so that's the m, the bound on the partial sums comes there. Okay. So this is important. This is going to give you a sector that opens in the half plane. Okay, that's what this is going to give you. If you want to keep this bounded, then that means your S will be going inside a sector, not otherwise. All right. Okay, so proof. So put an equal to f of n divided by n to the s naught a of x equal to summation an n less than or equal to x. Then a of x is less than or equal to m for all x. Okay? All right, so now what can we say about this? Observe that. Summation f of n over n to the s, n between a and b. Actually here he has a strictly less, I think that's because of the subtraction. Is equal to the integral from a to b 1 over t to the power s minus s naught d a of t. Oh, I'm sorry. I should call this t. D to the power. Okay, so you agree with this. So the dA will pick up f of n over n to the s naught. So this is going to give you at that point n to the s minus s naught, so you end up with this. So use integration by parts. So this is equal to a of x over x to the s minus s naught, evaluated between a and b, minus integral a of x. Now this is x to the power minus s naught. So when you differentiate, you get minus s naught, which is s minus s naught here. And then you'll get x to the power s minus s naught plus 1 dx. Okay, so 7 yields that this absolute value less than or equal to this a of x is no more than m at both at the top position and the bottom position. But I'm now choosing s to be bigger than s naught. I think I should say that somewhere. Yeah, so I got to say here where real part s is bigger than real part s naught.
You have it up there with sigma greater than sigma naught.
Oh, I have it. Okay. All right, so this is now of size a to the, at the bottom, a to the power sigma minus sigma naught, b to the power, but b is bigger than a and this is positive. So this whole thing is less than 2m over a to the power sigma minus sigma naught. And that one there is no more than s minus s naught. Your m comes out. And a to b. And now you can take the antiderivative of this, but with absolute value. Right? That's the absolute value inside. So this is 2m over a to the sigma minus sigma naught plus m absolute s minus s naught times this integral is 1 over, it's really, what is this? It is sigma minus sigma naught, and then I have to evaluate 1 over x to the sigma minus sigma naught between a and b. And it's that minus this, but then when I put absolute value, I take the sum, so I put a 2m over, and I'll get this a outside. Coefficient 1 here, coefficient is that. So that's what we get. So what does this mean? So the consequence, the important consequence, several. One of this is theorem 6. If summation f of n divided by n to the s, n equal to 1 to infinity, converges for some s equal to s naught, then it will converge in the half plane sigma greater than sigma naught. So, if the Dirichlet series converges at one point, it will converge at every point to the right of it. Why? Because if it converges at one point, then at that point it's going to have bounded partial sum. That's all is needed. But the moment it has bounded partial sums, we use this, which tells you that this quantity is now going to 0 as a goes to infinity, which means the Cauchy criterion is satisfied by the tail. And if the Cauchy criterion is satisfied by the tail, the series has to converge. The convergence of an infinite series is equivalent to saying that the tail satisfies the Cauchy criterion. Right? Okay, so that's the proof. Since summation f of n over n to the s naught is convergent, the series has bounded partial sums. Hence, by theorem 5, the tail of the series less than epsilon as a tends to infinity, right? Satisfies for sigma greater than sigma naught, satisfies the Cauchy criterion. or I should say, satisfies the Cauchy criterion in sigma greater than sigma naught. Times theorem 6. So what does theorem 6 imply? It implies that if summation f of n over n to the s diverges at sigma at some s equal to s naught, then it diverges in the half-life sigma less than sigma. So, using that same Lin-Sup argument for the set of values where it diverges, we conclude that there is a quantity called sigma c, which is the abscissa of convergence. So to the right of that, it converges in the ordinary sense. To the left of that, it diverges in the ordinary sense. So the abscissa of convergence need not coincide with the abscissa of absolute convergence. So the consequence is theorem 7. The Dirichlet series, each Dirichlet series, there is a real number sigma c such that the series converges in sigma greater than sigma c, diverges in sigma less than sigma c. Sigma c is called the abscissa of convergence. Clearly, sigma c is less than or equal to sigma a. But we will show that sigma a will be less than or equal to sigma c plus 1, right? That will come immediately. So we'll do that when we come back on, oh, sorry, I can't come back on Friday, Monday. But then we will use this criterion to get uniform convergence in a cone. It's a cone because for this to go to 0 uniformly, I have to bound this. But in order to bound this, I've got s minus s naught in the numerator, and I've got sigma minus sigma naught in the denominator. So I've got to have s minus s naught not grow much faster than sigma minus sigma naught, and that means the slope must be finite. So at every point in this cone, or the sector, this s minus s naught is like s sigma plus it, right? So so if this has got slope b, this will be no more than 1 plus b, and therefore this is bounded. So we first prove that there is uniform convergence in every sector, which means the function will be analytic in every sector, because we appeal to a theorem from complex variables that a uniform convergent series of analytic functions is an analytic function. So each function here is analytic individually, and is a uniformly convergent series because of this. And therefore, we're getting something stronger. Even in so in every sector, you will have analyticity, but I can go on increasing the sector. So the function will be analytic throughout the half-plane to the right. So Dirichlet series represent analytic functions in their half-plane of convergence, not just in the half-plane of absolute convergence. But we need to distinguish between the two, because when we do an Euler product, we have to go to absolute convergence. If not, it won't work in ordinary convergence. So we got to study where the connection between the half-plane of convergence and the half-plane of absolute convergence. Okay, so we'll do that.